Okay, hello everybody. My name is James Taylor, and I'm an engineer at Salesforce.com. And first, I'd like to thank all the sponsors for making this awesome event possible, and the selection committee for giving me the opportunity to talk to you guys today about an open source project called Phoenix, which puts a SQL skin on top of HBase. So before I get into it, I just want to give you a little blurb about me and a little bit about the history of Phoenix itself. So I've been working for the past 4 years on big data at Salesforce. And it's been an interesting ride. 4 years ago, we actually started to try to build our own big data stack from the ground up. And 2 years into it, right when our hardware arrived, of course, the project got canceled. We realized we were building something that looked an awful lot like HBase, and it didn't really make sense for us to try to build that without the awesome community that's behind HBase. So that became the birth of Phoenix. So prior to that, I was at BEA, where I worked in a couple different groups. I worked for Liquid Data, which is a federated query engine using XQuery as its query language. And then I also worked for WebLogic Event Server, which is has a CEP, complex event processing engine, and SQL-like language that's part of it. So that kind of gives you an idea of where I've been the past few years. Okay. Okay, in the dawn of time, there were relational databases. Relational databases were invented. But eventually, folks hit a wall when it came to performance, because data sizes got bigger than relational databases could handle. And then there was HBase, and HBase came along, and it was a good thing. It was a big improvement, the next evolution. It was horizontally scalable, so you could add machines and your application would actually become faster. It maintains data locality automatically for you. It splits your data and compacts it automatically, which is a great thing. And it runs on commodity hardware, which is a blessing. You don't want to have to buy huge, beefy machines to run your database software on. But somewhere, something terrible went wrong with HBase. Okay, it takes too much expertise to write an application in HBase. And it just takes too much code to actually do anything in HBase. I don't know how many of you here have actually used the client API in HBase, but the blessing is it's low level, but on the other hand, it takes a lot of code to actually accomplish anything. And third, in the end, your application is tied too closely with your data model. So it becomes difficult to evolve your data model because all your business logic and your data model is tied in very tightly with your code. Okay, so let's talk about Phoenix now. What is Phoenix? So Phoenix is a SQL skin on top of HBase that basically replaces the HBase client API with a new API that is nothing more than an embedded JDBC driver. And this allows you to run at HBase native speeds, because what Phoenix does is it compiles your SQL queries into native HBase calls, essentially so you don't have to. So there's no MapReduce involved. It's directly making HBase calls. There's no additional server hops because it's an embedded driver, so the client portion is running with the HBase client, and the server part is embedded inside of the region server through hooks that HBase provides called coprocessors and custom filters. So why does this matter? Well, in a word, performance. The top bar you see there is the performance of Hive, while the red bar and the blue bar, that's not the x-axis. That's the band of query performance you'll see with Phoenix. Now, you'll approach that blue bar if we were able to glean parts of your row key from your where clause in your query, your performance will approach that blue line, whereas if you're doing full table scans in HBase over Phoenix, then your performance will approach that red line. OK, so let's just step back and ask ourselves, why would you even want SQL on top of HBase? Why is that a good thing? Well, one big reason is to give folks an API that they already know. So I don't know about all the companies that you guys work for, but certainly with Salesforce, everybody knows SQL. And it's a big barrier to get them to try to use a new API that they're not already familiar with. So that's why we created Phoenix initially, and that's why we open sourced it. The second reason is to reduce the amount of code that a user needs to write. So I just threw this query up on the screen here, and it's nothing particularly fancy, but if you're familiar with the HBase client APIs, then actually writing the HBase client code to execute this query would be quite a bit of code to handle group by aggregation, calculating an average within that group, bucketizing things by date, and to do it all inside of coprocessors and custom filters would be even more code. So Phoenix essentially does that for you. The third reason of why you would want SQL on top of HBase is basically to perform performance optimizations transparent to the user. So with a high-level language like SQL, you're really just expressing what the data is you want to get. You're not expressing how you want to get it. So it gives you a level of separation there. A couple of examples are aggregation. So Phoenix executes aggregation on the server side. It pushes the computation to where the data lives. And the data that gets returned back to the client are the aggregated rows. So it's a much smaller data set, and it conserves your network bandwidth. Another example is our skip scan that we introduced in our 1.2 release of Phoenix. So this is a special custom filter that when you query over your row key columns, it will actually efficiently skip through the data by taking advantage of an HBase feature in filters that lets you skip from one point to a completely different point in one hop. A third example of a performance optimization would be creating a secondary index. So this is something that we're adding. It'll be available within the next month or so. And essentially, you'll issue a DDL statement, a create index DDL statement, and Phoenix will take your main data table and maintain a secondary index table from it. And then when you issue your regular query, Phoenix will decide with its query planner whether it should use the data table or the index table. So that's a good example of how performance can improve transparent to the user. And then a fourth reason is just to leverage the ecosystem that is already available in SQL. SQL's been around for quite a long time now. There's a huge ecosystem. And so now, with Phoenix being delivered as a JDBC driver, you can start plugging into those things. I just put a couple examples here. You can use a SQL client called Squirrel. That's an open source, much like, looks like Toad, if you're familiar with Toad. Another example is our terminal interface, which is called SQL Line, which is another open source project. It looks a lot like SQL+. And then other types of things are things like an OLAP engine. So we've got a guy on our mailing list who's taking Pentaho, which requires a JDBC driver to drive it, and he's plugged in Phoenix there instead of the Hive JDBC driver to reduce his latency on his queries. OK, so let's take a look at the data model for Phoenix. And I want to talk a little bit about how it overlays the HBase data model. So first, I'm going to go through explain what the HBase data model is, and then I'll show you how it relates to Phoenix. OK, so HBase has tables, so you define tables, and then you define column families. And then within those column families, you define column qualifiers. And then on top of that, you've got your row keys, and you've got your values that form your key values. Okay, so this is the basic HBase data model. And then another dimension on top of that is the multiple version dimension. This is the multi-dimensional aspect of HBase. So in HBase, when you update a value, the old value sticks around, and you can actually do flashback queries and access that data. So this is the basic HBase data model. Now, how does this map to Phoenix? Well, a Phoenix table maps one-to-one with an HBase data table. And then there are two types of columns in Phoenix. There's key value columns, which are one-to-one with your column qualifiers. And then there's your row key columns, which basically you define a row key as a multi-part composite key of all the columns that you want to put in your row key. Okay, now I want to talk a little bit about the metadata, the Phoenix metadata. So where does this metadata go that Phoenix keeps when you define tables and alter them? Well, it's actually stored in another HBase table that's somewhat hidden from you called system.table. And it's updated automatically when you run our DDL command. So when you create tables and alter tables, you're actually, behind the scenes, we're modifying that table. We keep the older versions of all your schema updates, and then what we do is we correlate the timestamp of your schemas with the timestamp of your data, so that if you issue a flashback query and connect it at earlier time, we'll actually use the schema that was in place at that time. And then finally, all this metadata is accessible through JDBC through the standard JDBC database metadata APIs. And one kind of cool thing is that since it's a Phoenix table, we've actually implemented those interfaces by issuing Phoenix queries behind the scenes. So next, what I want to do is I want to walk you through a set of 3 examples. And I want to explore how Phoenix does its query processing to give you a little bit better appreciation for what's going on behind the scenes. So the domain I've chosen, not the most exciting domain, but one that I'm sure you can all relate to, is server metrics monitoring. So in this case, let's say you have groups of clusters and you want to monitor them. So you've defined this Phoenix table where you put the host name, which is the full machine name, plus the cluster identifier as the host. And then second, you define the date. So you've got a composite key of those two columns. And then second, you've got your key values. These are all your metric values which you want to monitor. So GC time, response time, I/O time, things like that. And then let's say, for example, you've got this is some sample data where you've got your host name, which is, again, the first 3 characters may identify your cluster, followed by a dot, followed by like a machine name. That's an example of what the host would look like. And then the date is just a regular date to the millisecond granularity, and then you may have any number of metrics, say response time and GC time, and so on. Okay, so I'm going to walk through 3 examples. The first example is to chart the response time per cluster. So this is where you may want to produce a line graph like this that would show you what your average response time is across all the machines in all your clusters. Okay, the second example is to walk through, you want to find the 5 longest GC times. So maybe you want to produce a bar chart like this, where you've got the time identified on the x-axis, and you've color-coded your hosts based on color, and so you can quickly identify which servers are running into GC problems. And then a third example would be to identify the 5 longest GC times again, but this time, let's say you want to do it over and over again, so you want to optimize it. So those are the three examples I'm going to walk through now. Okay, so the first example. this is what the query would look like. Pretty ordinary query. You're selecting from your server metrics table. And let's say you want to look at the last 7 days worth of data. So you're taking the date, any date greater than the current date minus 7. And let's say you want to look at a subset of your cluster. So you want to look at the SF1 cluster, the SF3 cluster, and the SF7 cluster. And then finally, you want to group that information by cluster identifier, plus you want to bucketize the times into date bands, essentially. And then finally, you want to calculate the average, or let's say the min and the max response time. OK, so the first thing Phoenix does is it parses your query, and it looks for usages of your row key columns within your query. So in this case, it's found the host, and it's found the date. Now, the next thing it's going to do is it's going to identify the constants that you're matching against these particular row key columns. So in this case, you're matching against SF1 or SF3 or SF7. And then you're matching the date against the current date minus 7. So that I've just identified that as a T1, so anything bigger than that. So this forms a kind of matrix of what the possible query results can be. So the next thing Phoenix will do is it will take those kind of bands of data and intersect them with your region and your region boundaries. So in this example, say you have 4 regions and for your table, and now we've intersected those row key ranges and discovered that the query can only possibly take data from either region 2 or from region 4. So right there, we've ruled out half of the data that we're not even going to look at. So the third step is to execute a parallel scan across those 3 bands of data. So this is not something that HBase provides out of the box. They don't provide parallel scans. This is something that Phoenix added on top of HBase. So we're going to issue 3 parallel scans on the client side, and we'll push through a special custom filter called a skip scan. And what this is going to do is it's going to immediately look at the first row and realize that it's sitting in a row that's actually 90 days back, because that's how much data that you've got on your cluster. And it's going to immediately realize that it needs to skip forward to the current date minus 7. So it's going to skip all that data. And then once it reaches there, then it's going to start to include all of the data up until it finds another machine, in this case S2. And then again, it's going to start skipping that data because, again, it's 90 days back for the time component of your key. So it'll skip over all of that data, and so on. It'll just basically skip through the data that it doesn't need, skipping, say, 90% of your data. The next step is our aggregate coprocessor kicks in. So coprocessors are a nifty feature of HBase that gives you a hook into the server-side processing that is going on. So in this case, we intercept the normal scan of HBase, and we add a little more information that determines how we're going to aggregate it. So essentially, we push through the group by information from the query. So in this case, all of the rows that pass through that skip scan filter are handed to this aggregate coprocessor, and it'll condense those rows down using only the first 3 characters of your host name, because that's what you said you want to group on, and a day truncated version of your dates. So the rows that get returned back to the client are much, much less than would otherwise be returned. And then finally, the last step is that it performs a final merge sort on the client side and takes the results from all the parallel scanners that were run and computes a final aggregate based on that information. OK, now the second scenario is similar to the first, but it's a little bit different because in this case, it's not an aggregate query. It's a top-end query. So in this case, you want to find the 5 biggest GC times. So you're going to order by GC time descending, and you're going to hold on to 5 of those. So you're going to limit the query to 5. So in this case, the same thing happens as before, the same client-side and server-side processing that I showed you before. But in this case, instead of the aggregate coprocessor kicking in, our top-end coprocessor will kick in. And what this does is it just looks at all the data as it passes through, and it hangs on to the 5 rows that have the biggest GC time. And then those 5 rows are what gets returned as a result of this scan for this particular region. And then finally, similar to the other scenario, the first scenario, we do a final client merge step where we look at all the rows, at all 15 rows, and we choose the 5 of them with the biggest GC time. So that's basically how top-end works in Phoenix. OK, so the third scenario is much like the second scenario, but this time we want to optimize it. Let's say this has become a key criteria that you want to collect again and again. Maybe you have a monitoring interface. So in this case, we're going to create an index on your server metrics table. And we're going to index by the GC time descending and the date descending. And we're also going to include, to create a covered index, we're going to include the host and the response time. And the reason we're doing this is we've chosen to take a little bit of a hit at write time such that when we scan this table, we won't need to join back to the main data table. We can essentially issue a scan against the index table without joining back. So here's what the row key looks like for our index table, which is, again, this is transparent to you, but gives you an idea of what's going on behind the scenes. So in this case, the row key will lead with the GC time in descending order, followed by the date in descending order. We'll include the host in the row key because we want a one-to-one correspondence between an index row and a data row to ensure uniqueness. And then anything else that's included as a covered column will be included as a key value. So what does the query look like? Well, the query looks exactly the same as it did before. But in this case, what Phoenix is going to figure out is based on the query itself and the fact that you're ordering by the GC time in descending order, and the fact that that matches the leading row key of your index table, Phoenix will use the index table instead of the data table to run this query. And we'll essentially pick off the first 5 rows that we get, and we'll be done. So it'll be a very, very fast query. So what I'd like to do now is switch over to a demo. What I'm going to demo 2 things, actually. I'm going to demo the skip scan in action. So just a quick demo. I'm going to run 2 queries side by side so you get a feel for how much quicker it is if you use the skip scan versus a full range scan. And then the second thing I'll show you is just kind of a toy application that we put together, which is, has about 30 million rows. It's all running on my laptop, so not too beefy there. And it's basically, we've imported 10 years worth of stock data for the Fortune 500 companies at the hour granularity. And yeah, and I'll show you how interactive an application can be when you run it on top of HBase with Phoenix. OK, so this is using our SQL line interface that I mentioned before. And I'm going to go ahead and start this query. And then I'm going to come down here and start this query. So the bottom one is already done. That's using our skip scan. That took about half a second. And the top one is actually doing a full range scan, and that took about 8.5 seconds. So as you can see, the query didn't change, but the performance is dramatically different. OK, now I'll just switch over and give you a little flavor of this stock analyzer app that we have. So in this case, what I'm showing you is a graph of the average stock price for the tickers that I've listed here. So every time I make a change in this web app, it's actually running a Phoenix query behind the scenes. Now it's graphed every stock ticker that starts with an A. I can graph Apple, and then I can compare it against Google. I can downsample this. And remember, every click here is actually running a Phoenix query behind the scenes. So it gives you an idea of how interactive web applications can become, which is not the typical sweet spot for HBase. You can group by industry. Let's say I want to group by industry, and I want to show an average over all stocks. So that was pretty fast, and that shows you an average across all these industries. So that kind of gives you a flavor. It's kind of a toy app, but it does give you an idea of how interactive you can make applications that run on top of this technology. Okay, so what I'd like to do is I'd like to talk a little bit about our roadmap, just touch on a few items and kind of future directions, and then I'd like to open it up for questions. So I already mentioned secondary indexing. That's something that's in progress, almost done. Second item is joins. We're going to start with hash joins. A third interesting item is doing some integration with the Apache Drill project. There's a lot of potential synergy between Phoenix and Apache Drill, where Drill could execute kind of a many-to-many join and hand off each side of the query, if you will, to Phoenix, and Phoenix can quickly execute each of those queries and hand the data back to Drill, and it's a pretty good story for getting a kind of many-to-many join. Fourth one is enhancements to our aggregation functionality. So there's count distinct, which has actually already been committed in our master branch. Intel has actually joined our Phoenix team, which is exciting. They included Phoenix in their Hadoop distribution, and there's a team now from Intel, which is pushing forward with us and other folks out there to make Phoenix better. So this is an example of one of the things that they've contributed, which is great. Another item is derived tables, so you'll be able to nest selects within each other in the from clause, like I've shown you here. And then there's some bigger ticket items like a cost-based query optimizer. We've already started work on stats collection, which we'll do in HBase, and then we'll use that to drive optimizer decisions. So that's kind of a new horizon that can take kind of a lifetime, basically. Interesting area. And then there's the whole area of OLAP extensions with windowing and partitioning and things like that. That is a really good fit, I think, for HBase. And we'd love if one of you wants to help contribute, we can get you going. And other areas include things like monitoring and management. HBase has a lot of good monitoring and management tools already, but with Phoenix in the mix, you really need a monitoring tool that's at the level of Phoenix and that shows you, given a query, what all the scans represented that are running in that query. And you want to do things like roll up, like how much I/O time an entire query took. Because remember, we're parallelizing, and we need to collect that data from the server and roll it up to the client. And so there's a lot involved there to actually do some better monitoring and management. And then, the holy grail of transactions, that'd be an interesting one that's been tried before. So that kind of gives you an idea of Phoenix and the internals and how it maps to HBase. And now we have time for questions if folks would like to ask questions. Thank you very much.
Hi, I have a question. Can you elaborate a little bit on how Salesforce is using Project Phoenix? Like what kind of use case you're targeting?
Sure. So we have both internal and external use cases that are in the works. I'll mention a couple of the internal ones first. One is similar along the lines of the server metrics monitoring and trending and analysis. So of course, we have a lot of machines with a lot of data that we want to collect, and we want to use that data for trending and things along that nature. So that's a big area. Another internal use case is product metrics and product intelligence, where we basically pull information out of our logs to find who's using which feature to discover feature adoption, correlation between features, kind of stickiness, top users of different features and all that kind of stuff. I think our first external use case is going to be around data archival. So, of course, Salesforce has a lot of data, and one particular area that is starting to dwarf other data in the system is a change tracking mechanism that we have inside of Salesforce. And so what we'd like to do is we'd like to offload part of that data and actually store that data in HBase instead of relational system, and then as transparently as we can, still support the same APIs that Salesforce gives to its customers, which include things like SQL, which is a SQL-like query language. So essentially, we've got some glue code now in our application stack that will translate between SQL and SQL and execute Phoenix queries. So that's an example of, I think, the first kind of thing that you'll see HBase being used for in a customer-facing way. Question?
Yeah. Even though that was a toy application, the response time was pretty amazing. So can you tell me a little bit about how much data you have in there and how many column families?
Sure. Again, that is kind of a toy app, and it's running on a single machine. Everything's local, right? So we couldn't really do too much with it, but it's basically, it's a very narrow table because all it has is the stock ticker, and it has the date information, and then it has a kind of a classification of which industry it's in. And that's about it in terms of data. I mean, there's a fair number of rows because we've imported 10 years worth of data for 500 companies at the minute granularity. So that's kind of what I was trying to express. It's a single column family. Yeah.
So, but basically, this opens the possibility for using HBase in kind of real-time, interactive kind of dashboards and applications, right?
Absolutely.
Is that the intent?
Yes.
Right.
Thanks. Question?
Yeah, got a few questions. The first one is, do you have any plan to support a data binding schema?
Oh, that's a good question. Yeah, I didn't get into that. We actually do have support for defining a schema at query time. We have this feature called dynamic columns. And so it's interesting you start to a little bit to deviate from SQL standards when you start getting into stuff like that. But kind of our philosophy is as long as you can run a standard SQL query, it's OK to be able to augment for things like this. So what you can do at query time is after you list your table, you can, in parentheses, define additional columns. And then those will be just like columns like any other column, so you can filter on those columns and things of that nature. So that's one thing we support. And we support that at upsert time when you're inputting data, as well as at query time.
My second question is, because the HBase data model is like a NoSQL data model, it supports very flexible colon specifications, right?
Right.
In terms of performance, I believe that should have caused some extra overheads. In order, I mean, if your use case is a very traditional SQL model, is there any plan or any configuration to remove that overhead?
Yeah.
To support a more traditional, relational data model.
Yeah, that's a good question too. So one of the awesome things about this open source stuff in this community and working with HBase is the HBase community is really open to new ideas, right? So we're really getting a lot from that community, and I'll just give you a couple of examples of stuff that actually kind of was put in even before Phoenix, but we were really able to leverage it. Like they have these fast diff encoding, right? That's great because it reduces the size of your data, but you don't take much of a performance hit to compact your data. So that's one example. There's this tree or try encoding that was introduced that, again, is along the same lines. It'll compress your data. I expect, again, this is at the HBase level, but all of this can be exposed through Phoenix because when you issue your DDL statement, you can tack on properties, and those properties just get passed through at table creation time. So you can override your data block encoding if you want. And so I expect that there'll be more data block encodings that'll be more like columnar store type encodings that'll be support even faster scan times and better compression rates.
My last question is to enhance the join performance. Do we have any plan to co-partition the data because the HBase is really organized data set? So really we could afford to partition the data across nodes if we wish so.
Yeah, that's a really good question too. I think we'll start with hash joins, where one side of your join is small enough to fit into memory on a region server. And I think that solves a lot of use cases right there. So I think that's where we'll start, and a lot of the work is kind of in the front end and the query compilation and things like that. Once you build that in, adding new kind of join strategies is a bit easier. And you start to need stats, so we don't want to do too much too early because we don't have stats to drive these optimizer decisions yet. So we really need that in order to make better optimizer decisions. And then another thing, like I mentioned on our roadmap, is to integrate with Apache Drill, right? So that's kind of Drill's bread and butter, right? Is being able to handle huge to huge joins. And I don't know, I'm not convinced we want to reinvent that in Phoenix necessarily. We'll see how far down we go on that road. But we'd love some contributions if you have ideas.
My last question is a very easy one. It's, do you support mid-query failover? For example, you are running a query, a long running query, but the query, some nodes fail in the middle.
Right.
Do you fail the whole query?
The whole query fails.
Okay, there's
Yeah.
no middle query.
No.
Okay, all right, thank you.
Yeah, thanks.
So my question is, how would Phoenix handle a really wide table? Let's just say a table that has an indefinite number of columns. Would that be speaking to the dynamic column strategy, or is there a way to handle that?
So, yeah, that's a good question. So, dynamic columns is really meant more for kind of ad hoc querying. It's not really meant for the use case that you're talking about. We do have an issue that's open that's kind of an interesting approach to that, and it's basically, so once we get joins in place, then a lot of times these kinds of scenarios that you're talking about is where value information is encoded inside of the row. So you may have prefixed everything with a user ID followed by some standard suffix, and then so if you think of it, that's kind of like a join. It's like a parent-child join, right? So so once we have joins and we do that part, then I think you'll be able to express as a join between a parent table and a nested child entity, right? And you'll be able to basically operate on it that way. But
Plus, if you were doing joins, you'd have to have a way of adding columns anyway, right?
what do you mean?
I mean, just if you're selecting different columns from different tables, they have to be able to fit together.
Yeah, we already do that, but it's more about if you're doing that kind of, if there's lots and lots of columns within a given row, you probably want to do some kind of filtering on them as well. So you have to be able to express that in some way, and that's our idea. We think it might work.
Cool, thanks.
Yeah.
Have you run into any heap pressure issues with the coprocessors under heavy write load? Or to start out, how large of a data set and how large of a cluster have you deployed this on?
So our main use of coprocessors is actually on the read side of things, We're just now getting into coprocessors on the right side with secondary indexing, and we haven't put that through kind of a stress test yet. So stay tuned, right? I think it'll be okay. I mean, HBase has a reputation of being performant on write, but we'll see. There has been a lot of iteration on the read side to make coprocessors faster, right? Because if you think about HBase, even internally, it's got this scan API, right? And it's got this next iterator. But every time you go through that next iterator, it's doing quite a bit of work, right? But if you're sitting inside of a coprocessor, you don't even want to go through that, even though that's an internal API, because it's too much overhead row by row, right? So we have a couple of committers on our team at Salesforce, and they put in this internal next that we can use, and anybody can use, of course. We saw a pretty big jump in performance just based on that. So I think it's the two communities working together. They're really receptive to that. I think it bodes well.
Can you give us the size of cluster you've deployed this on and with how much data?
So our clusters internally are actually not that big because our architecture is a pod-based architecture. So we have pod by pods, which are big groups of machines, right? And what we're going to do initially is deploy an HBase cluster per pod, right? So it's on the order of, it's less than 50 nodes. So I guess that's on the, it's not huge.
Thank you.
Yeah.
Can you elaborate a bit more on the different components of Phoenix? I mean, what goes on the HBase nodes and what's on the client side?
Sure. So client side includes things like parsing of the query. We rely on Antler. We have an Antler grammar that we use to specify our SQL grammar. Then there's a compilation stage of that query that happens on the client as well. And then after that, there's kind of a runtime piece where the client needs to push enough information into the coprocessors that the coprocessors can do basically expression evaluation. So what we can do is we can serialize our expression and we can execute, we can do an expression evaluation on the server side.
So is there a separate daemon that runs on the HBase region server node, or
No.
just a coprocessor?
It's just a coprocessor, yeah, and custom filters, those two things.
So did I hear you say you don't do joins right now?
That's right, we don't do joins right now.
So, but your plan for joins is
Yes.
just to do simple ones that fit in memory, nothing larger.
Where one side fits in memory. So one side can be as big as you want.
Okay, so you have no plans to go beyond that.
We'll see.
Can you get a word more about your potential integration with Drill? Because I would think you would be competitors.
No, not really. So what Drill is relying on other storage engines to execute bits of its query, right? So Drill is not going to write HBase drivers to execute its query bits. It's looking for other parts of the community to provide stuff like that. So I think there's actually good synergy between those groups. Yeah. All right. Thank you very much.